Now this is our second lesson about the potentiometer wire. In the first lesson I talked about how to determine the calibration constant of the potentiometer wire. Probably I didn't mention that the galvanometer is a device that is used to detect presence of a current. When there is no current flowing through, the galvanometer shows no deflection. Now, there are various applications of the slide wire potentiometer. Among them are these mentioned over here. Determining the EMF of a cell, you can use it to measure internal resistance of a cell, can be used to determine a known resistance, to find the current flowing through a wire, to calibrate an ammeter and voltmeter, and also to measure the thermoelectric EMFs. We shall be looking at all these various uses one by one, so you don't have to worry about them now. Now, looking at the first one, how to determine the EMF of a cell using a potentiometer wire. In our circuit, we connect the circuit as shown on the left-hand side. We have ES as a standard cell and E is a cell of a known EMF. We have switch K, which is first thrown to position 1. When you throw it to position 1, only one cell is connected, that is cell ES. Then you move the jockey along the wire until the galvanometer shows no deflection. It means in the lower circuit, there is no current flowing, and therefore the PD across the wire AD is equal to the EMF of the cell. So that is why we say that ES is equal to KLS, where K is the PD per centimeter of the wire. Then the switch is now thrown to position 2, and the jockey again tapped along the wire until the balance point is obtained. So you measure the new balance length, and again cell ES will now be disconnected and it will only be cell E that is in the circuit. So the EMF is equal to KL. So dividing equation 1 by 2, we simplify and come up with the EMF of the cell as L over LS times ES. That is the EMF of a cell. We can also use the potentiometer wire to determine internal resistance of a cell. In this case, we need a resistance box. R represents a resistance box, which can be set at different values. But before including that resistance box in the circuit, we have the switch open, so that, and then we tap the jockey along the wire until a balance point is obtained. So we will get an equation E naught equal to KL naught. Then close the switch when the resistance is set at the minimum value, say resistance of 1 ohm. And then you move the jockey along the wire until a balance point is obtained. So that PD across the resistance is going to be equal to KL. Then now set the resistance to some other value, 2, 3, 4, and in each of those cases find the new balance length. So from the right hand side you can see the equations that come up, that if it is E, when the switch was open, we have I is equal to R into capital R plus small r. When the switch was closed, we have the PD across the resistor, which is V equal to IR. So if you divide that, on the right hand side, we had K L naught KL. So the K's cancel, you remain with L naught over L. So this on the right hand side, you remain with 1 plus small r over capital R is equal to L naught over L. So this simplifies to 1 over R into 1 over R small r into L naught over L minus 1. So if we plot a graph of 1 over R against 1 over L, we get a straight line graph, and using the slope, determining the slope from the graph, we can determine the internal resistance of the cell. Now, we can also find the unknown resistance using a potentiometer wire. In this, what we need to do is to first of all connect the resistor whose unknown resistance is required. Then with the switch open, we find the balance point. Assuming that E naught is a cell whose EMF is known, we determine the balance point first of all with the switch open. Then close the switch and again find a new balance point when the galvanometer shows no deflection, and also measure the current reading. So after you have recorded the current reading, you can now write down the equations. First of all, the first equation when the switch was open is E naught equal to K L naught, shown on the right hand side. And then when the switch is closed, V is equal to KL. So dividing those two equations, and substituting for V equal to IR, we get the value of R as L E naught over I L naught. So we have determined the unknown resistance in that way. Another method of determining unknown resistance is by having a complete circuit in the lower section as our secondary circuit, and two resistors R and RS. RS is a standard resistor, R is a resistor whose resistance is unknown. So connect the galvanometer at point B, which is between the two resistors, and then you tap the jockey along the wire until you get a balance point. So the PD that you obtain along the wire is equal to the PD across the resistor R. So we can now write the equation V equal to IR is equal to KL. Then we disconnect the wire AA, capital A, small a, and then connect it to point B following that broken line. And then remove the galvanometer from point B and put it at point C. And then you move the jockey along the wire and again determine the balance point. So when you do that, you get a new balance length. So the new balance length is equivalent to the PD across resistor RS, which we can call IRS is equal to KLS. So dividing the two equations, we'll be able to get the resistance of the resistor R, and it will therefore be equal to R is equal to L over LS times RS. That is how we determine the resistance of a resistor. Thank you for listening to